Hello, this is Mrs. Taylor, and I'm going to explain to you how to determine if a function has a vertical asymptote using limits. Vertical asymptotes can be found using limits. If a function is rational and can be simplified through factoring, it may have a vertical asymptote. So I'm going to look at this function, x plus 2 all over x squared plus 5x plus 6. And I'm going to look at two different cases, one where x approaches negative 2 and one where x approaches negative 3. Now, through direct substitution, if I substitute in this negative 2, I get in the denominator, I get 4 minus 10x plus 6, which equals 0. And so if I have 0 on the bottom, it's undefined. So the method that we learned in that case is to try to divide out factors. And so the denominator factors into x plus 2 and x plus 3. And then I see that my x plus 2 factors cancel from the top and the bottom, so that when I use direct substitution again, I have 1 left on the top, and then on the bottom, negative 2 plus 3 would be 1, so this limit would equal 1. So that's something we've already seen, and therefore, doesn't indicate a vertical asymptote because the limit exists and it is 1. Let's look at this case over here. So if I use direct substitution, substitute the negative 3, I get 9 minus 15 plus 6, again, add it all together will equal 0, so I need to try factoring out again. Well, we already know from the previous example that when I factor this out, I will have the limit as x approaches negative 3 of 1 over x plus 3. And when I use direct substitution, I get 1 over 0. And so our conclusion in terms of determining if the limit exists or not would be that the limit does not exist. Because I have an undefined answer, I can't factor anything out, and if I look at it graphically, I would see that there was a reason. Now, if you look at the top, we were trying to find vertical asymptotes algebraically, so let's not look at the graph yet. Let's try to draw conclusions without that. So, a vertical asymptote occurs where a function has a non-removable discontinuity. And when evaluating the limit at the c value, the result is a constant over 0. So non-removable discontinuity means that when I factor it out, factor the quotient, I can't remove the factors like I did with the first limit. So here, the x equals negative 2, that would be a removable discontinuity because I could factor it out. But here, x equals negative 3 would be a non-removable because it did not factor out. So this is a non-removable discontinuity. And once I evaluate this limit, I get a constant over 0. So that indicates that this is a vertical asymptote. So my conclusion would be vertical asymptote. And it's vertical, so the equation for a line that's vertical is x equals, so x equals negative 3. And if I look at the graph, I will see that as well. So that explains why the limit does not exist, because there's a vertical asymptote there. So let's look at one more case. If I am looking at this function, f of x equals x plus 2 over x squared plus x minus 2, question is first, where could there be a vertical asymptote? If I factor the denominator, I have x plus 2 over x minus 1 times x plus 2. And I see that the x plus 2 factors cancel. So looking at it as a limit, and I want to determine a vertical asymptote, the official notation would be limit as x approaches whatever the non-removable discontinuity is, which is x equals 1. So of x plus 2 over, and we'll just leave it in factored form, x minus 1, x plus 2, oops, forgot my plus, And then when I evaluate, I'm left with the 1, or excuse me, in this case 3. No, because these do factor out, so I'm left with 1 over 0, which is that constant over 0. The limit does not exist, but there is a vertical asymptote at x equals 1. So that would be how you would determine vertical asymptotes using limits.